Welcome students. In this lecture, we will try to analyze the time complexity for depth first search. Now, as I told you, DFS is crux of many graph algorithms that you will study further, like shortest path algorithm, Dijkstra's algorithm, and several other graph algorithms. So, understanding the time complexity of DFS is very important. If you understood it correctly, in future you can evaluate the time complexity of any graph algorithm. It won't be very difficult for you, correct? So let's start this understanding and analyzing this time complexity for DFS. So as you can see, the basic algorithm is written here and we have discussed it many times in our earlier lectures. So let's try to evaluate time complexity based upon this algorithm of DFS. Now, so basically what's happening, if you could see here, this we call this function DFS, and we pass our starting node here, starting vertex onto this function, right? So let's try to first evaluate this very function, right? Let's start with evaluating that how much time complexity does this function has, correct? Let's start with it. So if you see what this line is basically doing, it is nothing doing, but it is doing what it is doing. It's setting a position in an array to a true. So that is definitely a constant time work, correct? So it's O1. And now what is happening? This for loop is being run, and how many times it is iterating? Let's suppose say we don't know, and we say k times it is iterating, right? So for example, let's say k times, for this particular case, for the vertex v, this for loop will run for k times. And now what this for loop is doing? So this for loop is nothing, it is checking a particular condition, that whether a particular node has already been visited or not. It is checking this condition. So how much time will it take? Definitely O1. And then what is doing? It is doing, depending upon this condition, whether it is evaluated true or false, it is calling the same function again outsourcing the work, right? Okay, so this concept, I think we are on the same page, right? This is what is happening basically. Now next question will be, how many times this for loop is getting executed? It is getting executed k time. Now what this k is? So this for loop is being evaluated for all the neighbors which are adjacent to v, correct? So also how many neighbors are adjacent to v? It will depend upon the number of edges we have, correct? In case of a undirected graph, all the edges, and in case of a directed graph, only the outward edges, correct? But it will be equal to the number of edges this v has. This for loop will iterate, correct? So we can say now that this for loop, how many times it will iterate, it will be proportional to the number of edges your v has. So this k is nothing but number of edges of v, correct? Now our question is simply asking that how many times this for loop is going to be called. Simple. In each DFS, this for loop is going to be called proportional to the number of edges this v has, and how many times this for loop is going to be called. So as you know, this DFS function, from the trace of algorithm of this which we have studied in the previous lecture, this DFS function will definitely be called upon each vertex at least once. Not as at least once, but exactly once. 2 times it will not be called. And at least once every vertex will be passed on to this DFS function, correct? So it is, I think now it is safe to assume, correct, that this line will be executed the number of vertices you have, and this for loop, for every vertex it will be called. This is for sure now, correct? Because DFS will be called for every vertex in the graph. So this for loop will be called for every vertex, and for every vertex this for loop iterates how many times? The number of edges that vertex has. And this for loop, in each iteration, it does a constant amount of work. So what will be the total amount of work done by this complete DFS algorithm from starting to end? That will be somehow proportional to the total number of edges, right? Because each for loop is proportional to the number of edges each vertex has. It is being called the total number of vertex the graph has. So it is somehow proportional to the total number of edges we have in the graph. Not exactly equal to, but yes, proportional to. And that's what your time complexity is. So let me also explain you now. If you have not got this time, let me explain you in detail by taking an example. Because this concept is very important. I'm going to go slow over it. Slow. So now what's happening here, if you see this, first of all, I'll start DFS on this vertex A, correct? Now on A, I passed A here, correct? As I've passed A here. So how many times this for loop is going to iterate? The number of edges A has. And how many number of edges A has here? 3 edges. I'm marking it with the red, correct? And definitely this will also be called 3 times. So sorry, this will also be called 1 times, but this for loop will be called 3 times, correct? And it will so happen that all the time this for loop has been called, this condition will be evaluated to true, and 3 DFSs will be called, correct? 3 DFS on B, DFS on C, and DFS on D, correct? So let me write here also DFS with the different color, maybe this. Is it clear? Now let's evaluate each DFS from now. So now let's suppose let's take this one, the one which is called on B. So now when this DFS is called on B, so let me use the same color coding. So now B will be called. This will be visited. This statement will be executed constant amount of time. And now for how many times this for loop will be called? Definitely the total number of neighbors B have, and they are 2. So which neighbors B have? So let me make it by green. This and this. Now this condition this time will not get will not be set true for A because it has already been visited. So then DFS on A will be called, correct? But this much times this for loop has been iterated 2 times, correct? So if I make this graph for, if I make try to evaluate it, so for A, what has happened for A? If you see what has happened for A, constant amount of work has been done in this here. So O1 has been done here. And how many times this for loop has been called? So this for loop has been called, if I write it so like this, 1, 2, and 3 times, correct? So 3 times, and this is the constant statements because each statement is just evaluating this condition. So 3 times it has called. Now for B, how many for loops? So B, 1 constant amount of work will be done, and the number of edges for loop will iterate 2 times, correct? So it will, and each for loop takes O1 time. So this much time will be taken, correct? And now come to C. So now if you have come to C, now with the B, no from B, sorry, not C, from B you will go to E. E, how many times it will be called? E has only 1 neighbor. Now we go to E. E has only 1 neighbor, so it will be called only, for loop will iterate only once, correct? And this no DFS will be called because it has only 1 neighbor B and it has already been visited, right? So only 1 for loop is being called. Now what will happen? Now we'll go to C, correct? Now we'll go to C. and here we have C. Let me mark C with the black one. I'm going really very slow on this because this is very important. I'm going to see how many times this for loop will be evaluated. Definitely 2 times. Why? Because it has 2 edges. Correct. So for C, 2 times this for loop will be called and 1 times this DFS will be called. That will be on F. And when this DFS is called on F, how many times this for loop is going to be evaluated? For one time. Correct. And then no further vertex will be called. Correct. And similarly for D. So now what will happen? You'll backtrack and then you'll call D. Correct. So you will call now D. Now what will happen? Now D, this statement will be executed. How many times for loop will iterate when D is being called? Only one, because it is only one neighbor, right? So it will be called only once. And whether DFS will be called? No, because its only neighbor A has already been visited. So this will not be evaluated to true. Correct. So how many times now, as you can see, how many times this for loop is being calculated? Correct. It is nothing but the number of edges. First of all, number of edges A has, then plus number of edges B has, then number of edges E has, plus the number of edges C has, plus the number of edges F has, plus number of edges D has. Correct. And also for every vertex this statement will also be called, right? So for each of them, constant amount of work, the number of vertices there are, it will also be called, right? So I'm just not writing it because it's a constant amount of time, so it will be O1 only, right? And this is what? This is proportional to the total number of edges this graph has. So our complexity for this complete, this complete function being called again and again until our DFS finishes, it will be O times E. Are you getting this point? I'm not saying exactly E. If you count these colored threads, this will be the total number of times the for loop is getting executed. This is not equal to number of edges E, but it is proportional to the number of edges, right? By O means, we mean the proportional. So as the number of edges will increase, these threads will also increase, and it will be directly proportional to E, not to the square power of E, not to the cube of E, but linearly proportional to E. Correct. Now, second part of the algorithm is, are we done yet? No. There is one more small thing which we need to keep in mind. What? The initialization. So, first of all, before even evaluating passing the start vertex to this DFS, we have to initialize the visited array, all of the locations of this visit array to false. And how much time it will take? Tell me how much time it will take? Order of V, because V are the number of vertices. That much time you have to access this array. Correct. So what will be the total complexity here? So what will be the total complexity here? So if I write the total complexity, it will be order of, definitely this V plus order of E. So I can also write this is nothing but equal to, if I just rub it, so the total complexity will be nothing but order of V plus E. So this is your answer. So for the DFS, the time complexity is V plus E.